Related rates. These are some marvelous applications of implicit differentiation. We're going to spend about 2 weeks working on related rates problems. Here's your first example. A spherical snowball is melting at a rate of 1 centimeter cubed per minute. At what rate is the radius decreasing when the radius is 5 centimeters? Spherical snowball. 1 centimeter cubed, that means the volume of a sphere. If you look that up on the internet, you'll find this equation. The volume of a sphere is 4/3 pi r cubed. We're looking for a rate. Now, a rate of change is a derivative. So we're going to take the derivative of both sides of the equation, and the question is, with respect to what variable? If you guess v, I'm afraid you're incorrect. If you guess r, you're also incorrect. Pi is not possible. Pi is not a variable. And 4/3 is not possible either. So this is not obvious. Let's go look at the rate that we know. Centimeters cubed is volume over minutes, that's time. So the rate of change is going to be with respect to time. How did we know that? When you normally write dy dx, it's what's in the bottom that tells you what to take the derivative with respect to. What's in the bottom? Minutes, which is time. So we're going to take the derivative with respect to t. How do you do that when there's no t's in the equation? You use implicit differentiation. You take the derivative of v with respect to v and chain that with the derivative of v with respect to t. The end result of that is you get the derivative of v with respect to t. Taking the derivative of the other side of the equation, the variable here is r, so we'll take it with respect to r, and then chain that with the derivative of r with respect to t. That will end up giving us the derivative of 4/3 pi r cubed with respect to t. Derivative of v when v is your variable is 1 times dv dt. Derivative of 4/3 pi r cubed. R cubed is the only variable here. It'll be 3r squared, and the 3's will cancel out, giving us 4 pi r squared. Bring down the dr dt. Let's look at that again. Derivative of v, where v is your variable, is just 1. Just 1. Bring down the dv dt. Derivative of 4/3 pi r cubed, derivative of r cubed will be 3r squared, and the 3's will cancel out, giving us 4 pi r squared. What are we solving for? What rate, that means something to do with d's, is the radius decreasing? So radius, so change in radius. Change in volume, change in radius. So we're looking for dr dt. So we're going to move the 4 pi r squared to the other side of the equation. Now let's see what we know. Spherical snowball melting at a rate of 1. So we can put the 1 in. And because it is melting, it's getting smaller. It'll be a -1. R would be 5. So we'll put 5 in for R. Let's check that again. Change in volume over time. Melting at a rate of 1 centimeter cubed per minute, so losing 1 every minute. R, 5, we'll put that in. 5 squared is 25, times 4 is 100. And then we'll write a sentence. The radius is decreasing at a rate of 1/100 pi centimeters per minute. So what happened to the negative sign? The negative sign is taken away and replaced with a word. If you say decreasing at a rate of -1/100 pi, they would cancel each other out, and you'd mean you're really increasing. So to keep it very, very clear what's going on, we're going to use words instead of negatives. Now you're only allowed to put the word decreasing in if there is a negative here. If there's no negative, you would tell me it was increasing. So make sure you catch that melting means getting smaller, and the negative means it's decreasing. Now, the good news about this section, The method is the same for every single question. The equation will be different, but the method is the same. Start with an equation that relates the variables: volume, radius, sphere. Volume of a sphere with the radius involved. Take the derivative of both sides of the equation with respect to t. Almost all your questions will have time in the denominator, so almost all of them take it with respect to t. After you've taken your derivative, identify what you're looking for. If it asks for a rate, we're looking for something with d's in it. Rate of change of radius, so that's the change in radius over time. We get that by itself. Then look for any information that you can plug in. And once you've plugged in that information, clean it up and write a sentence. Let's try another one. A woman walks east, north, south, west, east. So a woman walks east. A man leaving at the same point walks north. But what rate is the distance between them changing? So we're going to draw a diagram. The woman walks east. The man walks north. Distance between them. It's a very good idea to put variables on sides that change. For those of you tempted to put numbers on, I'd suggest you wait. If we put numbers on, it can get really quite confusing. So variables for sides that change. We need an equation now that will relate these variables. Right angle triangle, Pythagoras. We'll take a derivative, and that'll give us some rates in our question. So why is this called related rates? We had an equation that related the variables. Now we have an equation that relates the rates. Derivative of x squared, we take it with respect to x and chain that with dx with respect to t. Derivative of y squared, we take it with respect to y and chain it with derivative of y with respect to t. Derivative of z squared, take it with respect to z, change it with derivative of z with respect to t. Why with respect to t? Because it's over time and it's over time. So it's the change with respect to time. Clean these up. Derivative of x squared, you know, that would be 2x. Derivative of y squared would be 2y. Derivative of z squared would be 2z. Now, what are we looking for? At what rate? That means d's are involved. Distance between them changing. So it's the change in z we're looking for. So it's dz dt that we want by itself. Divide both sides of the equation by 2z. Got these 2's that are common to everything. If we divide the 2's out, we'll get a simpler equation. We can keep our numbers small. Now let's find some numbers. X is the distance the woman walked. She was going 2 meters a second, and she went for 1 minute. Watch the units: minutes, seconds. So 1 minute is 60 seconds. So in 60 seconds, going 2 meters every second, she'd end up going 120 meters. 2 meters, a minute worth of seconds, so 2 meters per second times 60 seconds, 120. The man walking at 1.5, 1.5 meters every second for 60 seconds, that will give us 90. Our right angle triangle, 90, 120, if we use Pythagoras, we'll find out that z is 150. So we put those numbers in. X became 120, y 90, z 150. Now, dx dt is the change in x. How fast was the woman walking? That would be 2. dy dt, how fast is y changing? And that would be 1.5. So the 2 is the change in x, how fast x is changing. 1.5 change in y, how fast y is changing. We have just a bunch of numbers on this side of the equation now, so we'll just simplify. You can use a calculator. For those who don't want to use a calculator, I would notice that these numbers, 120, 90, 150, can all be divided by 30. Then we get 8 plus 4.5 over 5, 12.5 over 5, 2.4. Now, positive numbers, so the distance is increasing. Why were all these rates positive? This distance was getting bigger. Bigger means positive. This distance was getting bigger. Bigger is positive. Should Z have been positive? Is that distance increasing or decreasing as these two people walk further and further away? I think it's increasing, so this should make some sense to you. In terms of the units, what would Z be measured in? That is a distance, and we were measuring distance in meters. T is time, and we were measuring time in seconds. So that's why the distance is changing at 2.5 meters per second. 2 questions for you. The radius of a circle is increasing at a rate of 3 centimeters squared. But what rate is the circumference changing? Circumference circle. 2 pi r. If you're not familiar with that formula, you can always look them up on the internet. We're going to take the derivative of both sides with respect to t. When you do derivative of c, do it with respect to c first and change it with derivative of c with respect to t. That will give you derivative of c with respect to t. Derivative of 2 pi r we'll take with respect to r because that's the only variable we have. And we'll chain that with derivative of r with respect to t. End result will be the derivative of 2 pi r with respect to t. Derivative of c with respect to c is 1 times dc dt. Derivative of 2 pi r would be 2 pi. R is to the power 1, multiplied by the 1. R becomes to the 0, so you're just left with 2 pi. What are we looking for? Rate, so that's d something. Circumference, rate of change of circumference. So no rearranging necessary. So what rate is the circumference changing when the radius is 5? Nowhere to plug in the 5, so let's keep looking. This is the rate of change of radius, which was 3. So we'll put that in. 3 is the change in radius. And so we end up with 6 pi. Units of measure, circumference is a distance around, and we were measuring distance in centimeters. T is time, and that would be seconds. So the circumference is increasing at 6 pi centimeters per second. Let's see if increasing makes sense. The radius is getting bigger. As the radius gets bigger, the distance around is getting bigger. It was a positive 3 because it was increasing. Positive answer, increasing. Time for you to try it on your own. What rate is the area changing? First thing you need to start with, area of a circle. Pi r squared. Take the derivative of both sides of the equation with respect to t. Try it on your own, put me on hold. Let's check the answer. Derivative of a, we'd take it with respect to a first and multiply by the derivative of a with respect to t. That will end up giving us the derivative of a with respect to t. Derivative of pi r squared we'll do with respect to r and multiply by the derivative of r with respect to t. That will give us the derivative of pi r squared with respect to t. Derivative of a with respect to a would just be 1 times dA dt. Derivative of pi r squared, bring the 2 down. 2 pi r, lower the power by 1. So there's our 2 pi r, bring down dr dt. What are we looking for? At what rate? So it has to involve the d's. Is the area changing? So that's dA dt. When the radius is 5 centimeters. 5 can now go in for r. We didn't use it last time because there was no r anywhere in our equation. dr dt and r are very different things. dr dt is a rate of change. R is simply the radius. Let's check again what we're doing. We're doing r is 5. The r dt change in radius is 3. So r is 5, dr dt is 3, 15, 30 pi. Units for this one, area. Centimeters squared for area. Volume would be cubed. Circumference is just centimeters, so be comfortable with your units. Time, seconds. So again, area, centimeters squared for area, and increasing because everything is positive. Think it over again. If the radius is getting bigger, is your area getting bigger or smaller? Definitely bigger. Your job today on page 4 and 5, we have 10 questions for you to do. If you have trouble, go on to the collaboration site. See if anyone else has already asked the question. Get a friend, work together on it. Ask me questions. I am happy to help you. The beginning of this section, sometimes people have a bit of a struggle, but the more questions you do, the easier it gets. And often this is the test where we get the most 100s.